Today, I will present our work Convex call approximation for activation functions. This is joint work with Zihan, Wang, and Professor Guangdong. Neural networks are now fundamental in vision, language, and control systems. For example, traffic sign recognition and robot control system. They are powerful, but this wide usage also raises reliability concerns. In safety-critical domains like aviation and autonomous driving, we need neural networks to be 100% correct, even under small perturbations. This is why verification matters to ensure robustness formally. Here is an example. In the picture, this is the ARCA's XU artifact collision avoidance network, a classical verification benchmark. So what is neural network verification? Neural network verification checks whether a model always behaves as expected. Formally, for all inputs in a region, the outputs must in a safe region. So it's about proving the network is always correct under certain inputs. Next, what to verify? A common goal is local robustness. Small input changes shouldn't flip the prediction. We test if all perturbed samples within an epsilon ball are classified the same. This ensures the model is stable to tiny noise. So how to verify neural networks? The main idea is that we estimate output ranges based on bounded input ranges. If our estimated range fully contains all true outputs, it's sound. Exact matches give complete verification. However, there are some challenges because there are non-enumerable perturbations and non-linear activation functions. So we need to handle this by building linear constraints that describe all variables. Then we infer safe output bounds symbolically. This picture shows different mainstreamed methods on neural networks verification. Different methods trade off precision and efficiency. For example, MILP-based methods are exact but very slow. Relaxation-based methods are fast, but they are not always precise enough. So recent work like Prima and ReLU here, they utilize multi-neuron constraints. These methods proposed an idea to construct some non-trivial constraints for neural network verification. Most verifiers use single neuron constraints. They are only about one activation functions with one input and one output. But tighter bounds need multi-neuron constraints across several neurons. It means we will consider multi-neuron at the same time with multiple inputs and multiple outputs. Our work focuses on making these higher dimensional halls efficient to compute multi-neuron constraints. In this work, we aim to over-approximate the convex call of general nonlinear activation functions because there is another work has contributions to over-approximate the convex hull for ReLU functions, and this work we aims to handle the cases of the other activation functions. For example, we handle 3 categories. The first one is ReLU-like functions, like ReLU, leaky ReLU, or ELU. And the second one is like S-shape functions. They include sigmoid and tanh functions. And the third one is multi-variable functions like maxpool. They have multiple inputs. And this work proposed a method called ReAct. It means wrapping the activation function whole. First, we give the problem formulation. We take as input a convex polytope region, typically given in constraint form. Our output is another polytope, also in constraints, that covers all pairs of input and outputs. In simple words, we want a convex wrapper around the function's true nonlinear surface. Like in these pictures, showing the examples of ReLU surface and ReLU hull, and tanh surface and its hull. In summary, we approximate each activation function host using double linear piece functions. We also call them DLP functions in the following sections. So they only have simple 2-segment linear curve ways that let us convert the nonlinear function into something almost like a ReLU, much easier to handle. In these pictures, the green surface is DLP functions. Specifically, the step 1 is to construct DLP functions as bounds for an activation functions. We position the inflection point carefully. It means here in a 3D view, the inflection point is a line. We position the inflection point carefully, ensure both soundness and tightness. This replaces the complex nonlinear function, the right surface, with 2 simple linear segments. Like in this picture, we use 2 DLP functions. One is as the upper bound, and another one is for the lower bound. The step 2 is to over-approximate the convex hulls of DLP functions, shown here in the blue one. This step is efficient because we reuse the machinery of our earlier method ReLU, designed for ReLU functions. So by this way, we can construct we can handle the simpler DLP functions rather than the complex original activation functions. And this way is very fast and efficient. The step 3, finally, we extract the active linear pieces, the blue patches. It means we need to choose some useful constraints or sound constraints for the convex call of the original function. This gives us the final convex call that tightly covers the activation function. Depending on the output sign, we know which constraints to keep because one DLP function is for the upper bound and the other one is for the lower bound. So we can easily choose the correct constraints obtained before. The above example shows the case of time h functions. For ReLU-like functions, the precise simplifies. They are almost convex already. So one DLP bound is enough. Similarly, for max pool, all inputs are non-negative, so we can use some inequality to construct the function home. Overall, our method has been extended to multiple activation functions, and it's very efficient and effective. For the evaluations, the first part is to compare our method with the SODA convex over-approximation method. From the figure, we can see that our method is more efficient and precise. Also, we need fewer constraints. Next, we implemented our method into the neural network verification framework. This is about local robustness verification, and you can see that in these figures, we can obtain more verified samples with less runtime. Thank you for listening. Welcome. Any questions?
Hey, thanks for the talk. I wonder why did not you compare to alpha beta crown, which is the state of the art now in verification? Did you consider comparing to it?
Sorry, consider what?
To alpha beta crown.
Yeah, alpha beta crown.
Yeah, the state of the art in verification.
Okay, alpha beta crown is a very classical method, and it focuses on single neuron constraints. So this is where it's different from our method. We consider multi-neuron constraints.
Okay, thank you.
Thank you. But we also compare the alpha crowd. Yeah, you can see the specific results in our paper, maybe.